So today we have Professor Gita Sukthankar from UCF joining us for a talk on multi-agent systems. So Dr. Gita Sukthankar is a professor in the computer science department at the University of Central Florida. Dr. Sukthankar received her PhD from the Robotics Institute at Carnegie Mellon and an AP in psychology from Princeton University. She is a recipient of AFOSR Young Investigator, DARPA CSSG and NCF Career Awards, as well as numerous UCF awards for research excellence. Her current research centers on multi-agent systems, computational social science, and human robotic interactions. She has served as chair for various conferences, including AMAS, AAAI, etc. She has also edited many books, and feel free to chat with her post the talk, and we are open for questions through the talk as well. So thank you for joining us. Over to you.
Yes, thanks so much for hosting me here. So I gave this talk the very general title of Data-Driven Social Informatics, which encompasses kind of all of the research projects in my lab. But what I'll be talking about today is the set of projects that have to do with human-machine teaming. But before I get started, I thought I should tell you something about UCF because you've probably never heard of my university. It's actually the largest university in the United States now with 68,000 students. It's the 12th largest producer of computer science PhDs in the US. We have a very large funded research program and a CS rankings of 55 within the US based essentially purely on research productivity. Kind of our specialty areas are optics, photonics, modeling and simulation. I have a courtesy appointment with our modeling and simulation department. We have an excellent center for computer vision research. And very importantly, we have a new initiative in artificial intelligence, and we are hiring for the AI initiative at all levels, faculty, postdocs, and grad students. So our faculty search is still ongoing this summer. If any, I think it'll probably shut in the next month, but if any of you are interested, please tell your friends and check out aiucf.edu. So I've personally been at UCF since 2007. I direct the Intelligent Agents Lab. And essentially, I look at the applications of AI and machine learning to all these social computational systems. Essentially, what I'm talking about are these systems in which humans and agents are working together and often really interacting through social media platforms or online games. So usually our methodology is we gather a tremendous amount of data from social media, surveys, user experiences. We do a bunch of user studies. We apply machine learning to some of this, and our goal is really to come up with a predictive social model of how these systems will behave. And we look at these systems at a number of different scales, like huge social media platforms, smaller teams, individual users. And so I've graduated 15 PhD students. These are my current students who've contributed to my research. So the motivation behind this talk is really about human teamwork. And I'm sure all of you have the experience of working in a human team, possibly a research team, in which everything has gone wrong. So I got these figures from Ofer Amir and this great figure that shows that essentially you can have a team and everyone is working in a different direction. Our goal is to get to the point where all the team members are working in a coherent way toward a common goal. And the current technologies have enabled highly distributed teams. And this trend was greatly accelerated through COVID. So basically during COVID, all these people who used to be working together in person are now coordinating on Slack, Skype, GitHub, Google Drive. And so we have these ubiquitous virtual teams, but it's very difficult to get these teams right. And this has been kind of a problem in management science, in business schools, and kind of now we can see a definite retreat from virtual teams as most of the large tech companies have kind of given up on the concept and are bringing people back to office, but still the necessity for these hybrid teams remains because you always have collaborators in other areas. So our goal is to really to be able to study these human teams to understand what makes them work well and to look how we can use AI in this. So kind of one solution that's been posited is this idea that we are going to have proactive assistant agents that are going to help these human teams. And these assistant agents have been very successful to some extent in individual user interfaces. When you pick up your phone, when you use your Alexa, your proactive assistant agent now is really coming into reality. You want to take some of those same technologies and apply this to the support of human teams. It just becomes a more complicated problem because we're no longer modeling that one individual, creating that personalized model, but we have to model what's going on in the team. And a lot of this work derives to very early and well-cited work in the multi-agents community by Milind Tambe, and he created this system, TeamCore. And TeamCore had a couple of aspects to it. So one idea was that agent systems needed to coordinate and adopt the same ideas that human teams do. But the other idea is once you had that you could then essentially incorporate the humans right back into that agent team in a very smooth way. So the idea is that people would have their own little TeamCore wrapper, and that would enable them to communicate with the team. So this is not a new idea at all. It's an old idea. However, what's kind of changed is now we have a tremendous amount more data on the operation of teams. So what I'm going to be presenting to you is very much a data-oriented study on this. So I'm going to talk about these kind of three things, and I'll try to stop for questions in between these three logical breaks. So what I'm going to do, oh, did you have a question there?
Yeah, so I was wondering whether in the previous slide you had some like architecture that's presented. So this is quite centralized in the sense the team has a central director, which is like
right. So this is not my architecture. This is the Tambe architecture, TeamCore, and I guess these original architectures had this concept of a middle agent that acted as kind of a directory system that helped the other agents meet up with each other. This diagram was taken from the coordination of agent-based systems project. So the idea is the middle agent would enable all the other agents to intelligently find each other. So in theory, they were supposed to be robust to distributed failure. So actually, this project was also funded by DARPA, and DARPA did this kind of test where they knocked out kind of different agents in this to see if it would still work. So I think in practice, a lot of these researchers always kind of had one point of failure, but in theory, you could have a very distributed system that would be robust to this. That's a good question. So what I'm doing is, I'm going to talk to you a lot about software engineering teams, because this is, a point that, everyone's very interested in. We're all out there developing software. We're working with collaborators, and we really want to understand how to make those teams as effective as possible. Then I'm going to present to you some work that we did on creating new sequential pattern mining work specifically that we developed to look at team sequences, which are kind of by their nature a little bit more complicated than other types of sequences because you have the intermingling of actions of different people. And then the final work that I'll talk about is drawn from the natural language processing world, looking at specifically team communication. So looking at analyzing team communications to see if we can predict conflict and disagreement. And we think that this is a key thing to be able to do to create this proactive assistant agent. So I'm sure all of you, yes, are hopefully familiar with GitHub and use GitHub a lot. So you're all familiar with GitHub. You probably are busy manipulating the files and looking at the version control. For this study, we're really looking at these kind of social events and interactions. So we don't do any study of the code directly, but we're looking at those interactions. And this data set was provided to us by Leidos DARPA. They gave us a very large anonymized GitHub public event data set. We later collected more data from GH-Torrent. But in some sense, you can actually really think of GitHub as being a software social network. So you're all familiar with Twitter and this concept of following, retweeting, and liking, but essentially you have some of that same kind of social dynamics going on in GitHub as well. So users are interacting with these code repositories, that there are repository interactions that have more to do with popularity, people watching the code, forking it off. And then you have these kind of working interactions, contributions. So I'll be talking about these working interactions. But you can basically create from this these little event timelines of what people are doing. So when someone is going and branching off code and committing changes and then finally submitting a pull request and going through and discussing these proposed changes. So, and basically what we do is we're looking at that event timeline. So each GitHub repository, even though you might not have thought of it this way, in some sense represents a human team out there somewhere. And for this study, we were particularly looking at team formation. What happens when a team is just getting started? So we look at the first 6 months of events. We looked at essentially then after looking at the formation phase, we look at the next 7 months of what people are doing. And we consider a team member if they're sufficiently active. So they have to have pushed enough or had 5 accepted pull requests. We look at specifically work events. There's a lot of passive stuff that you can do in GitHub, and we looked at that as well. But we look at specifically those kind of work-related activities of pushing, merging pull requests, commenting on issues, and pull request review comment. So we are really looking, so for this study, we measure the performance in terms of looking at the amount of work that's occurring. And we also look at sequences of events that could be extracted at the team level, and we try to omit events that are inserted by automated processes such as bots.
This is for like a pre-specified project.
So we started working on a pre-specified project. So this project was originally funded by DARPA's social simulation program, and they wanted us to study the dynamics of cross-platform propagation. But I thought, wow, this is such a great data set. I want to go off and do other stuff with it as well. So then we started looking at software coding teams as kind of a purely like unfunded effort. And that's when we collected our own data.
But this is like the team here is working. They haven't given a particular, they have a target software in mind. This is not a bunch of coders trying
No, it could be that essentially we try to filter our repositories to only include coding repositories rather than general version control of documents. Okay. It includes a lot of, I'm a group of students and I've, looked at a project, and then also those very large open source projects. That's kind of why one of the things we did in the study was we tried to like divide up like teams into kind of like small teams, medium teams, and large teams, in which I think we had like large teams as greater than 10. And basically we looked just very simply at the division of work events and doing a median split and saying, okay, what are the differences between these teams? So one concept that people have is that in order to be productive, that you need to distribute the work across more individuals. And it turns out that actually, for better or worse, high-performing teams have higher levels of centralization. So sadly, the high-performing teams are apparently a few star programmers carrying everyone else around. We also looked at the efficiency in resolving issues, so that people who actually were issuing more work events also were resolving issues more quickly. So that we felt was promising and showed that our study was useful. So we took a look at the types of ways that people use GitHub. Yes?
So how do we understand Gini index? So is it like a measure of variance?
It's a measure of basically like if you look at like the 10 people like in the work events, how evenly it's like it's distributed versus having the one person who's contributed all versus. So work centralization means it was kind of the work, more centralization means one person.
Right. So smaller teams, so to understand that graph, smaller teams are, I mean, they split work more evenly, but
Yes, that's true. That ends up being true. Yes, definitely that's true. I think the as those teams become larger and larger, you're getting much more in terms of water. Whereas since the small teams are groups of like 3 people, that definitely that's more evenly distributed. So we tried to look at how people use GitHub, that there are definitely different usage styles in terms of how much people are pushing versus commenting versus collaborating. We did some work on clustering and we found these different stylistic ways. There's definitely a lot of variation in terms of how people are using GitHub as a system. And we looked at things like other types of patterns. So one thing that we were very interested in is burstiness, which is the measure of temporal correlation of activities. So how closely you're seeing this temporal clustering of events. And then we also looked at things, whether they were labeling issues and tagging them. And we did like a large data study on what human teams are doing in GitHub. But then basically the question that we were very interested in looking at is that, so for our original DARPA study, they were very interested in filtering out repositories that used bots. So GitHub bots are kind of any type of automated processes. And usually what these automated processes are doing are things like coding support, testing support, or possibly user support, where they're onboarding new users. So DARPA said, that they wanted to filter this out, but we realized that they were giving us this kind of perfect little example for looking at how do these repositories with bots differ from the repositories without bots. So essentially that we had been given this data set, we went and we also created additional data sets. We had some students hand tag our own repositories and kind of read the issue comments. Some of the repositories are explicitly tagged with the automation. We also created a classifier that could pretty accurately, with an F1 score of 0.93, filter out bots. And this was our data set, the one that was produced by DARPA, the one that we created ourselves, we hand tagged, and we propagated the labels elsewhere. Then we started to look, okay, how are work events differing in these human-only teams and human bot teams? And yeah.
What's the sense of the corpus here? Like the fact that you have to build a classifier means that this is a big, huge data set?
It's a very big data set, and it's like essentially, I guess the original data set that we got from DARPA was kind of like terabytes of like stuff. I mean, I guess the original GH torrent, basically it's a little complicated because when you pull data from GH torrent, you're pulling like a specific slice of data. You're pulling the events from that slice of data, so that if there are repositories out there, but if they're not represented, if they're inactive through your date rate, that they may be out there on GitHub, but they were entirely dormant. So in some sense, these numbers reflect like the active, the people that were active during that 13, basically everyone that was active during that 13-month window of GitHub. Yeah. And so one thing we realized is that basically that all levels of human bot teams, small, medium, and large, that they are churning up more of these work events, so that they're more kind of aggressively using the push, merge, pull request, issue comment. So at least by that measure, they are more productive. Then we looked at two.
Is this like worth asking whether this is a causation issue?
Yes, there's definitely the one main thing about this study is that all these groups self-selected to use automation, and that probably represent the more expert section. And what we tried to do is we tried to filter. What we came up with was an expertise balancing measure. So we kind of downsampled. So we had few repositories with bots. lots of repositories without bots. What we tried to do was create a matched expertise sample where we tried to match the age of the repository, the number of programming language, and look at that sample. That's absolutely, we really don't know correlation, causation. So I tried to do a really controlled user study. I was telling your students about this, in which we had our computer science programming classes at UCF use bots. So I had a senior design group, and they created some bots, and we tried to introduce them. And we found out that none of the students were that interested in using any of our automation types. So it was kind of disappointing, and that essentially what we've kind of realized is that the bots are really helping you in things like making sure certain security measures are done. So one of the results is the bots don't seem to be evenly distributing workload across the team. So one of the things the undergraduates, when they created the bots that we use, was they thought it would be great to kind of force some amount of work upon each of the programmers. So one of their bots was trying to even out balance. We have actually found it doesn't seem to be the case. They're not evenly distributing workload. Interestingly, the bots don't yield a clear speed up in issue closure. More issues are documented by the bot human team, so that they're definitely, the presence of bots forces people to use GitHub more aggressively. So it leads to the more generation of more code related events. The issue reporting system is used more extensively. So I think what the bots are doing is they're creating better explainability or readability of what's going on. They are not balancing the work on that. The main caveat being that the teams that use extra automation are the more expert ones. Controlling for expertise seems to reduce but not eliminate the teams. Yes?
There's one notion of like better execution, so efficiency, which is what you're measuring. But is there also another notion of fairness? Because you're saying that on one side, if the issues are sent to the more productive people, they get resolved faster.
We were actually, I think the undergrads essentially, when we tried to design the bot for use in the undergrad class, what they were trying to do was to, like, as issues came up, like, they just kind of have a queue system. So issues would go to, like, get assigned to, like, new people. I don't think that they for instance, they didn't delve into how long is each issue taking to, like, resolve or anything like that. But again, our problem was that generally people were not that enthused about using this automation at all. So we had to kind of settle for this in the wild study. But we were very interested in the idea that the bot is changing the rhythm. So it's probably modifying the event sequence. So we were looking at, do these sequences of events from bot human repositories differ? So we looked at things like looking at the sequences and measuring the silhouette scores between the groups with bots, the bot human teams, and that the groups are relatively distinct. We also said, okay, we can pretty reliably train classifiers to do this thing, so that from looking at the sequences, you can pretty quickly tell whether a bot has been used in it. And we also did, and my student became really interested in diving into this sequence analysis problem. So we started using this technique called a matrix profile. So the matrix profile, and I'll talk about this a little more later, is essentially summarizing all the distances between all possible subsequences. And we looked at concepts like, when essentially, if the matrix profile average is higher, it indicates the sequences in the group are a little bit less repetitive. Essentially, that the distances are a little bit greater, and they're greater because the sequences aren't repeated. So we noticed that we did see some differences in the average matrix profile. So our conclusion was there was quite a bit happening at the sequence mining level. Human bot teams have fewer repetitive subsequences because I think the automation is effectively removing them. in terms of complexity, that the sequences are equally complex. But my students said, really, we need to dive down and say, how has this changed the workflow for that programmer? So we started looking at creating new sequence pattern mining techniques. And at that point, we got a new challenge domain. So we got this new project from DARPA on looking specifically at human teams who are playing Minecraft. So a very kind of classic laboratory setting where we have 3 players playing Minecraft. They have to coordinate. And since this occurred during COVID, it was all done online, so all done over Zoom and online players. And we looked at really how these teams behaved. And we started the process of trying to create agents that could help these human teams. But we were very interested in knowing, okay, so can we use some of the insights that we got from the software engineering teams and look at them in Minecraft? So Minecraft, under the hood, I assume that all of you have kind of played Minecraft in some capacity. But essentially underneath what's happening is Minecraft is generating lots and lots of sequences of events. So as your players are moving or interacting with objects in the world, you can see clearly what they've done. And there's been a lot of work on sequence mining in games and looking at keyboard input, mouse input, work that's been done in StarCraft. Kind of the problem that's come is that this ends up being problematic for very long sequences. So we can get long sequences really quickly. We simplify things by trying to collapse some of the position data so we don't get really, really long sequences of movement. And also a problem is sequences with vague boundaries end up causing issues. Sequence mining, unfortunately, has not been used much in human research studies. It's a tool that psychologists are largely unfamiliar with, but that essentially some work has been done. Pentland did some famous work that on looking at sequential changes in work processes and found that variability was generally negatively related to performance. So this is we believe, a useful tool. It's been underutilized. So we started looking at how could we dive into these sequences and extract the actual differences. So what we looked at was going down and trying to find the exact subsequences in these longer sequences of Minecraft events that were different across different teams. And the possible applications for this are things like behavior recognition, that you could have this large data set, and then you might want to do something like build a plan recognition system. You can kind of go through and from the data set extract these repetitions. We were interested in studying differences between kind of our successful and our non-successful players. So the assist study that we had this idea of successful teams. Successful teams were ones that were doing well on the mission. The mission that they were given in Minecraft was to search the map and rescue victims. So we wanted to look at a few of these differences. Now, kind of to clarify, you're all very familiar with substrings, which are kind of these exact matches that are contiguous. Sequential patterns are also exact matches, but encompass like non-contiguous cases and can be effectively extracted with grammars. Yes?
What is collaborative means?
So for collaborative, the data set that we looked at, and I'll go into it later, was a group of people who were spontaneously playing Minecraft. So we had 2 data sets to look at. One in which we kind of had a classic human subject experiments. We get 3 people and we force them to do something. But then we also got data from a Minecraft server and looked at kind of people who are choosing to interact with other people. So we were looking at the differences between the people who are choosing to interact with other people as kind of quantified by essentially things like proximity and communications. And so, yeah. So the final idea, though, motifs, which are very popular in the bioinformatics area, where you're having something that's short and contiguous, but you're allowing for the non-exact matches. So here we have ABD, and that's allowed as a match for ABC because most of it is matching. So it has kind of a soft threshold that you have to set. So the data structure, as I mentioned.
All of these kind of do the opposite of what you want. Like all of these are measuring similarity, whereas you're
so what we do is the following. So we're interested in this idea that we are detecting the contrast between two different groups. So we have two groups and we believe that they're different on some dimension. So we separate the data and then we go back and we try to find the subsequences or the motifs that are common in that group and are not common in the other group. So that's the idea of contrast. I think here I have this. So contrast, so in the classification category, you're taking the attributes, your feature vector, and you're predicting a category. Here we're saying that we have some information of the category from some external source other than the subsequences. So obviously, you know, for our thing, we have this concept of score, so we can say high scoring, low scoring, what were the differences? So going back and saying, what were the actions that those more collaborative players are the better scoring? And that's what the contrast mining does. And so there has been prior work on contrast sequential patterns, not so much work on contrast plus motifs. So what we did for this, again, we go back to the matrix profile, which is a data structure developed by Eamon Keogh's group. And essentially what the matrix profile is showing is that given that you have a given sequence and then you break it down into a specific window length, so here is a window length of 3, you can have all these subsequences. And essentially you're creating the matrix profile by sliding this along and kind of essentially, and this is kind of denoting the position and that this is noting kind of the cost of the match. So obviously EAB is matching very well here, so that has a match of 0. Then you're basically going through and you're sliding this through that. Essentially, these things are all the different sequences in our data set. So here we have 4 total sequences in our data set. We have these subsequences, and we're looking at the profile between the motifs and the sequences. If we have kind of a case, which is essentially the minimum best match, if we have a case where we have a very low area under this curve, then that indicates it's a good match. So here we have ABC, which ends up being a good match, and you can see is exactly found in 3 of the sequence and partially found. So there's been a lot of work done on using matrix profiles, and this is kind of a pretty simplistic algorithm for going through and looping through and doing this iteration. So our goal is essentially to use the data to pull out these motifs from it. So we're trying to essentially do this process that we have these interesting subgroups of objects, and our goal is to identify the motifs. And essentially, a contrast motif is not selected simply because it's frequent. Essentially, it has to be frequent in one subgroup and uncommon on the other, and that's what makes it contrastive and useful. So essentially, what we're doing, very simply, we do the matrix profile, and then we do a statistical significance test on the differences. So extremely simple. So just to show again what the deal is, let's say that we've divided up group 1 is our successful players, group 2 is our unsuccessful players. You can find these orange, gray, and yellow subsequences in both group 1 and 2. But you notice this gray sequence really is just common through everywhere, so you want to ditch that. And that's basically what contrast motifs help. And that's what makes it very valuable as a tool for analyzing these platforms. Otherwise, you're just inundated by all of those million, okay, the software engineer checked in this, checked in that. So using contrast motifs, we're then able to pull out. So we divide our data set again, and then we see that the humans have this kind of simplistic pipeline. They're just pushing, creating, pulling requests, and the human bot is really forcing this kind of more complex comment pipeline. So it's really helping the humans annotate what's going on. It's forcing the issue comments to be made. Interestingly, the issue comments in total don't occur in higher frequency through that class of data set. So it seems the bots are forcing these intermittent issue comments. We also looked, yes?
Are the bots pushing the comments?
So they do different things. Each of these bots do, that there's, we didn't control what bots people used. And so some of them are code coverage, some of them are issue support. But I think commonly the way they are talking to the programmers is by creating issues. And so they are creating issues. It seems that they are, a human programmer is more likely to just commit, and make the bots are kind of forcing some addition of issues that are interspersed through it. So we also looked at this very nice data set created by, I think, Disney Research Zurich, Heapcraft, where they left a Minecraft server alone. They collected 2 months of data from 45 players, and they also asked the players to periodically annotate what they were doing. So in their kind of simplistic Minecraft scenario, they had these kind of divided up the data set into building activities, mining, exploring, and fighting. And we were able to use their data set and break it down. And using and doing our contrast motif mining again, we were able to create, essentially to identify what does fighting look like, what does mining look like, what does building look like in the Minecraft world. So essentially at the end of this, and this is probably what would make an excellent basis for a plan recognition system, because you can see what the players are actually doing. So we have these 7 different fighting motifs, these 2 mining and 3 building motifs, and you can look at the average distances. So fighting had more contrast motifs. There were more variations in fighting style. For exploration, there was no real consistent motif. Yes?
I'm probably simplifying here, but in the previous example of GitHub, can you think of this bot as sort of managing the team by creating?
Yes, I mean, in theory, it is managing the team. It's trying to manage the workflow of the team. But on the other hand, I don't know that that's the way the software engineers think of it, as the bot as the manager. They probably think of it as the bot is nagging them, and they have to quickly make a issue comment to get on with their work. So yeah, it might just be nagging them. So we also looked, one of the things that the Heapcraft data set, so the Heapcraft researchers were interested in the idea of collaboration. So they came up with this idea of collaboration graphs. They collected position information, communication information, and they had information on this. So we were able to go ahead and extract a collaboration graph of the players in their data set, just the way they described in their original paper. Effectively, the collaboration index is just counting the amount of contacts with other players and then normalized by the active players. We only looked at the top 10% of players as being collaborative. So then we said, okay, are there kind of special teamwork things that people are doing? And then disappointingly, we found that the motif that's common is fighting. So essentially, unfortunately, in Minecraft, if players are together in an area, that even though that this is, interacting with other players, that those players are much more likely to be fighting with people. And we didn't find a contrast motif for the less collaborative players. And we also tested this, that usually what we tried to do is we use kind of the full sequential pattern mining search, which allows for gaps and things, and we weren't able to get the one we were evaluating against to complete. So DARPA had challenged us to take a look at their specific problem. I don't think I'll bother with the video since you're probably familiar with Minecraft. Kind of hesitant to see what this does. Maybe we'll no. But what essentially they asked us to do was to study the data from their data set, which was a kind of forced team of three players pulled together for this 2-hour period. And we wanted to look at what makes some of the players better. So we started looking at differences in the movement, and this task essentially had the the players were called upon to rescue victims, so that they were running around the map, they were rescuing victims, they had to communicate with the other players about what they were doing. So essentially, we were able to create these sequences of kind of their victim rescue policies, and we created the contrast motifs. So what we did was we decided that we would look at the top performing, the top 30% scorers. And there was a fairly simple metric used to look at how successful was the team at creating the map and rescuing people. We ignored kind of the middle performers and looked at the low performers on this. And we looked to see how exactly they tackled this mapping strategy, and kind of this is the map that they were going around, and we looked at patterns in terms of what they were doing. And we found that the high performing participants all fell into kind of a few different patterns. So we had 3 versions of the map, in easy, medium, and hard, and we found these kind of motifs where essentially the player is very successfully, the team is successfully rescuing all of the victims in this order. An interesting thing was what we'd hoped to find was we'd hoped to discover that low performing teams were running into specific problems, that we could find a sequence that you could use to say, okay, this team is now messing up. We need to jump in and our agent needs to help. Unfortunately, we didn't find any contrast motifs. So remember, even though there are 2 classes, it's possible that contrast motifs may exist for one class, may not exist for another, it may exist for neither classes. My student kind of was looking and kind of at this, and she summarized it. I think that this is something that economists have said, but there is a novel written by Tolstoy, and at the beginning it has this quote, "All happy families are alike. Every unhappy family is unhappy in its own way." And he proceeds to write about this unhappy family. This is the Anna Karenina principle. But essentially the idea is that the success is achieved. Sometimes the path to success is very narrow. There were only a few ways you could be successful in this. There were many different ways to fail. And because there were many different ways to fail, we couldn't extract contrast motifs. So this kind of our finding, which we presented to DARPA, was that proactive assistant agents might have an easier time identifying people that they should leave alone than necessarily saying, okay, this is what you're doing wrong now, but that we can at least identify who you should leave alone.
This is not sufficient for you in the sense that because there's a middle range which in the sense that if you want to, one way to identifying a low performing team is to say that they're not high.
To use that, basically what we were concerned that essentially the closer the more of that middle data you incorporate, the harder it is to get motifs out of it. Yeah. That's kind of why we're trying to really look for the best example rules. I'm sure if we had incorporated the middle data, it would have been even worse. But essentially, this we feel is a useful tool. We've used it in a few other projects. If you're interested, we've made the code available. Essentially, it is encapsulating what makes 2 action sequences different. Yes.
So this essentially is another way of classification, right? So
not really classification. It's more like saying I have some groups that I've made the division in some other way. What was the reason that, which part of the data set, what made them different? That's the contrast.
Yeah. So let's say once you identify the motif, whether they followed the motif or not can be used to classify successful.
Yes, that's true. Basically, and that's where we think, essentially what we'd envisioned, that there was another performer on this DARPA project that had this plan recognition system, is you'd mine first and then you'd create at that point you have these little essentially kind of a finite state automata, and then you could make it into a more formal plan library, make a little strips plan, and then apply all sorts of recognition systems. But often the problem is that you have a plan library and someone has to author it. This is kind of a pain. Someone has to write down, how do you explore? How do you fight? This way, we're getting it in a bottom-up way. So that's kind of one way. So for the action recognition, exploring, fighting, mining, you could definitely see once you mine this, you can then create a recognition system to
The
do.
reverse problem.
Yeah.
So first you start identifying the contrast motifs and then the reverse problem of what you should
Right.
do.
Honestly, though, I think that the issue is the contrast motifs are a more explainable reason. I think that generally we were beaten by other kind of deep learning models that kind of non-explainably used in LSTM to like segregate this. But it provides a way that you can explain what's going on and that you can more logically do like some kind of knowledge tracing or coaching, which you can't really do with those other systems. So yeah.
This is a more like widely applicable idea in the sense that you can use these contrast motifs even for, let's say, distinguishing like Twitter threads that are like, more biased, but like
Right.
more
Yeah. Any
constructive.
kind of distinction should be doable, and definitely that there are probably other different statistics, like depending on how your data worked. Like we use the Mann-Whitney U-test because that seemed appropriate. There are probably other ways that you could decide this. So it's a relatively general framework. We were just interested in its applications to teams. So the final thing I'm going to talk about is very logically, you should be able to look at team communications. What are these people saying to each other? And we have communication data from a few of the data sets, including GitHub, which has the issue comments. And very logically, you have this communication between teammates, you have this multi-party dialogue, and hopefully your assistant agent can like jump in and be able to interject and say something in this conversation. So my student, Aisha Nayat, who just graduated last month, did a lot of work in this area. So we use this idea called dialogue acts for breaking up the text. And so what we did was, rather than treating all the text as a very, very long sequence, what we were doing is we're breaking up these different utterances into essentially kind of the function that they serve in the conversation. So things like statement, non-opinions, questions, acknowledgments, and we had a fairly simple machine learning classifier to do this. There's a very large switchboard data set, and this classification scheme that we're using was developed the SWITA tagging system. So we did some work on improving the classification. And then what we do is we take the team communication and we look at the sequences of utterances. We looked at a few different data sets. Of course, we had to look at our favorite GitHub data set, but we had an excellent data set from Diane Littman's group at University of Pittsburgh. And it was great because she did a very comprehensive human subject study where they did pre-task and post-task questionnaires. In particular, they did a lot of analysis on conflict. Conflict is what happens when you have team members that are disagreeing. Process conflict is about disagreeing on how the task should be executed. Now, all of these data sets that we're looking at are these fairly formal small group tasks where everyone's agreed they're working together. And my student did a lot of work on ways that you could predict team conflict combining multiple features. So the first thing that we're getting is for each of these utterances, we're tagging to a dialogue act. And so we're looking at the sequence of statements, questions. This is what theoretically psychologists believe is the basis for good teamwork. We also looked at sentiment. That's extremely easy to pull out. And we looked at this concept that Littman's group was very excited about, entrainment. Entrainment is this idea that psychologists have noticed that team members will adopt similar speaking styles. It's kind of interesting. And so you can actually look at syntactic entrainment, which is when people are using kind of similar amounts of verbs and so on in their phrasing. So we looked at essentially trying to look at the data set and trying to predict at a relatively early point how the teamwork is going, because we think that that's really crucial for to decide on the intervention. And as I mentioned before, for one of the data sets, we had these surveys in which the team members themselves rated the team on how much disagreement. For things like the GitHub data set, we had separate coders who would read the issue comments and make a decision on that. So from our preliminary analysis, we could see pretty clearly with this high conflict, low conflict division that the utterances that with more negative sentiment, more likely found in high conflict, and also poor communication indicators. Cases where people didn't understand each other, other kind of hedging, all of those things more likely found in the high conflict class. This gave us some confidence that these features would be valuable. Now, here's the basic problem with teamwork research. The problem with teamwork research is it's really hard to collect data from teams because you have to do your task. You have to convince 3 people or so to come to your lab and do your task. That means all these data sets are very small, usually less than 100 examples. However, there are teamwork examples from lots of different domains. So then the question is, how successful can we be at domain adaptation? So that we have these teams and that there are things that good teams have in common. So one of the things that my collaborator, Florian Jens, had said is that loop closure, this pattern of questions followed by acknowledgements, is something that should be found more commonly in good teams. This idea that one team member asks a problem, expresses it, another team member acknowledges it. Unfortunately, we tried to extract that pattern with our contrast motifs. We're not able to reliably pull that out, but that is kind of one of the theories. So our hope was we could create a more generalizable representation of team communications, and that we could learn it on one data set, and then it would generalize to other data sets. So that's kind of why we're starting at these more generalizable features, things like the dialogue acts and sentiment. We also ended up using text as well. It ends up being that text still remains useful, even though a problem is that the text from one of the data sets, text from Minecraft, does not look the same as text from GitHub. So our goal is, so we did a study on domain adaptation, whether we could learn. The team's data set was divided up into two sets. We were looking at to see if we could learn models on one of the data sets and evaluate it on the second part of the team's data set. This is an extremely easy domain adaptation problem, but also on the more challenging assist, Minecraft, and GitHub software engineering. And we looked at comparing against these baselines. We had a different classifier that used it in entrainment. We looked at BERT, which it was the general way that people would do that. And we also looked at other work that people were doing on domain adaptation. We found this one specific model that had worked pretty well for us by Bailey and Chopra, few-shot learning. It uses kind of a meta representation acquired using word2vec. And then we kind of looked at different variations of that. So we did a long study on looking at the use of synonym replacement, looking at the use of embedding learning. We essentially, my student developed this one representation, MFE embed, multi-feature embedding, and we used it both raw, we used it in a number of different settings, and we also used it as a replacement meta representation for FS text. We also did some more theoretical analysis on the generalization properties of the embedding versus other options, which really has to do very similar to this silhouette score thing where you're looking at the different representations and seeing how separable that they succeed. So synonym replacement, a very common strategy, what you're doing is you're augmenting your data set by just shuffling out some of the words. In a very simple way is to use WordNet. You can also essentially use synonyms that were drawn from the different data sets. So that's kind of one thing we did. So we did a very large study on looking and seeing how can we push this generalization model. We generally found that few-shot learning was very promising, and we could improve it using the multi-feature embedding. You can also use multi-feature embedding in kind of a simplistic, just use it along with a standard classifier. We also looked at other ways of learning a concatenation ensemble using LSTMs. So we did a lot of study on it. In general, we found that it demonstrated superior generalizability. As I said, we did some theoretical analysis on looking at silhouette coefficients. It's an excellent representation choice for the meta training stage of few shot learning. So kind of our recommended thing, which we said, is that if you're doing few shot learning, you could use MFE embed. And so if you're interested in this, you can definitely look at our code. You can also enhance performance by task specific synonym replacement. However, I will say that, of course, large language models have entirely changed this research area. So when we started on this project about 4 years ago, we were doing work with BERT. And so we looked at BERT and also the variations on BERT. Now LLMs make synthetic data augmentation super easy. So you can actually kind of generate, fake team dialogues, kind of. We haven't had a tremendous success on it, but we haven't done that much work on the prompt engineering side. But I'm pretty sure that we can ditch our whole synonym replacement stuff and come up with a much better augmented data set. So definitely that's kind of one focus of my work. I do a lot of other work on human-machine teaming, trust and automation, and I am so happy to be on sabbatical this year. So I will be on sabbatical this year at Harvard in the fall with Milind Tambe's group, looking specifically on the coordination of medical teams. So we have some funding to study how medical teams cooperate to deliver patient care, and that's something that Milind is also very interested in. So thank you so much for hosting me. I will take any other questions. Yeah.
So I had a question regarding the first project on Gita. So the way I was thinking about it is there is this bot which is nagging users to go and fix issues. And one way to think about it in the fairness domain is to think of it as assignment of chores.
Right, yeah.
So you don't want to assign too many
right.
of these nagging requests, and at the same time there is a certain efficiency gain to be had by assigning chores to the most efficient.
Right.
So is there any sort of thoughts on how to resolve that?
Honestly, I have no idea, because every time I have a theory as to what people will like, they usually don't like it. So I think so for that project, I mentioned that so there's some standard automation tools that you can use in GitHub, but I had a team of undergraduate software developers, and I let them come up with ideas like, what do you think would motivate you? So they had, one person had a gamification idea that they felt that there should be a leaderboard. Other people disagreed because they felt it would just, create the million stupid commit, player that kind of commits. But one person wanted to gamify. One person wanted to have a daily reminder, like a task list. So every morning that you had kind of the summary of what you had to do and the overall status. I think basically one person was we were just using one of these issue kind of insertion bots. We didn't do anything with code coverage or anything like that. But I think that at the end, I'm not sure what teams of software engineers would. Our basic allocation scheme was very, very simple. It's really just you do kind of a round, you rotate, the first person gets task one, the second issue gets, goes to a different, person, and so on. So not really looking at the status of task completion. But honestly, no one ever used our system enough for us to kind of measure how well it worked. So.
Yeah, thanks for that. So I had a question on the last project as well. So right now language models are so big.
Yeah.
To add to what you said in your future website. So if you directly ask the language model, here's a dialogue, is there conflict? Do you think it can answer this?
I wasn't actually, that I had never considered doing. I was really, my students have really just been looking at our problem before was we didn't have that much data, and now we could have a lot of synthetic data. It's interesting to see if you gave it a longer sequence, we haven't tried doing that. That's very interesting. Yeah.
what is a formal definition
A formal definition of which? Yeah, I mean, that's not something that we basically, that it's a kind of a relaxed subset. So it's continuous, but allowing errors, and then you have to decide yourself on kind of the threshold for how many errors to allow. Oh, yes. I mean, basically, we are totally copying what has been done in the bioinformatics community. So basically, my PhD student had done some work in bioinformatics, and she's like, oh, the bioinformatics community has a million like sequence pattern mining methods, and we have all these sequences. So I want to start using those methods. So basically, the like prefix span is a fairly generic one. So here's kind of the problem we had. So when we went back to bioinformatics, we found out that a lot of them are kind of gene specific, that they embed the biological knowledge in that. So that we had to rule out all those toolkits that did that and come to the fairly simplistic ones. And that was kind of our major issue. But definitely there's been a lot of like work in that. I think that the problem with social media sequences is they're a lot longer than the bioinformatics sequences. So a lot of the, I mean, some of the sequences are pretty long, but you know, people interacting in a social media platform can quickly generate like a lot of events. So all these things that were designed for shorter biological sequences then choked when we tried them. So I think we could have overcome them had we assigned a level of abstraction ourselves. So had we been able to, you know, kind of abstract and say, we can take, you know, these 7, and you can kind of do that in GitHub. You can look at like batching a string of commits, but without ourselves imposing a abstraction, we couldn't use a lot of the bioinformatics ones. But they are definitely the kind of the leaders in kind of that research area. Absolutely. Yes, I mean, basically a lot of the, you know, that they've done, you know, complexity analysis, they've done explainability analysis. It just, and I thought that we might just be able to get one out, but more often what they do is they prune based on biological restrictions. So they cut out things, and that we don't have that kind of, you know, nice domain knowledge. Yeah, that's a great question. Contrast is something that contrast sequences are something like that other people have done work on. This contrast motif, I guess people haven't usually, but there's work on motif mining, there's work on contrast. This essentially was something my student said, okay, I think that this is useful, and then she came up with this kind of specific extraction technique. Yeah. Yeah, but there's been a lot of work on contrast mining in general, like finding differences. More commonly, they use the subsequence, which is essentially allowing for gaps in the sequence versus motifs. Yeah.
The AI medicine, right? Like the last point.
Yeah, that's a new grant that we have for the National Institute of Mental Health. And what they want us to do is they want us to, that it's a subcontract with UC San Diego, and they want us to provide basically methods advice for medical researchers who are funded through that center. So basically, that people kind of often say, hey, I have an idea for a new evidence-based practice for we're going to be improving the mental health of teenagers in school. They write a grant to the center. But essentially what our job is to provide new techniques. So essentially natural language processing has not been used very much. And so I work with some psychologists who do shared mental model measures, so that essentially that there are all these ways to kind of quantify how teams operate, and that they want to apply these to these mental health teams.
What would be the data set there?
I don't know, because we just our funding just started in January, so we've had talks. No one has been brave enough to like bring a data set and say, I want your help consulting on this project. Yeah, essentially what we've done is we're supposed to be creating like a series of webinars to train people in our tools. So my student created a collab notebook to kind of for non-programmers to extract dialogue acts and things like that. Essentially, the dominant method that psychologists use is a system by Pennebaker known as LIWC, Linguistic Inquiry Word Count. And what they do is you create a dictionary of what you think valuable words are, and then it just, the Luke software goes and word counts it, and then you can say how many, and that's how, so they don't use embeddings or dialogue acts or anything like that. And then after looking at that, then the psychologists do their statistic tests and on that, and we're trying to improve their kind of usage of NLP.
Okay, if there are no more questions, we will just thank the speaker, and I'll request Professor Siddharth to hand over a token of our appreciation to Professor Gita.
Thanks.
Thank you so much.
Oh, thank you so much. This is great. Thank you so much.
Think they can,
I hope this t-shirt is of the right size.